Hello guys, I'm Jabin. Welcome to my channel. All these years, I've learned so much from YouTube, and I think it's time for me to share something with you as well. Hope you can enjoy it. So the first topic is about ADAS. We will discuss its basic theory and then do some practice. In the theory part, we will firstly give a brief introduction to ADAS. What's ADAS? Why we need it? Then we will use an example, ADB, to demonstrate the ADAS. ADB consists of 3 components. We will discuss them one by one individually. And last but not least, the communication between these components will be discussed. Then in the practice part, we will use Simulink to simulate the whole ADB system. So ADAS, what's ADAS? ADAS is short for Advanced Driver Assistance System. It helps the driver to drive safer and easier, especially for the green hands. But what kind of system can be considered as ADAS? Actually, ADAS is a general concept. Any system that helps us drive better can be considered as ADAS. For example, AEB, Autonomous Emergency Braking. Imagine that when something or somebody suddenly appears in front of the car, and the driver is however not able to react that fast enough, then what happen? Crash. So in this case, the AEB will hit the brake in time to avoid crash. Second example, lane keeper. The system is designed to ensure the car stays in its lane. If the car deviates from its lane, the lane keeper will take steps to correct it. A third example, adaptive lighting. Adaptive lighting, more general speaking, ADB system. This system adjusts the shape of the lights. Will do it automatically. The target is to create a glare-free driving beam. At the meantime, to maximize the lighting area. About this example, we will discuss it later in detail. So, what do these 3 examples have in common? Another saying, what kind of components are essential to an ADAS system? So, in the first place, the system needs a sensor to detect the environment before it makes any further decision. The sensor can be a camera or radar, or combine both. After the environment is clearly detected, the system will make decision what to do next. For example, in AEB, if the detection says there is a car in front and very close, then the decision will be hit the brake immediately. The decision making is made in controller. After the decision is made, the actuator will execute it as the final step. So hit the brake. The first 2 components are similar to almost all ADAS systems. A camera, then a controller. What difference is the third component, the actuator. It depends on the usage. An AEB is a braking system. In lane keeper, it can be the steering. In the ADB system, it's the LED matrix. In the following slides, we will use ADB as the example to demonstrate the ADAS, because I'm currently working in this field. So ADB, what's ADB? ADB is short for Adaptive Driving Beam. More generally concept is intelligent headlight. the target is to create a glare-free headlight. So in the conventional headlights, there is a high beam and a low beam. The low beam can be used anytime you like, but high beam not, because the high beam glares. It may dizzy the driver in the car ahead and cause accidents. So the high beam must be turned off in many scenarios. But if you turn off the high beam, you cannot get the best view anymore. With high beam, you can see, let's say, 200 meters wide. Without high beam, maybe only 50. So to solve this problem, the ADB system is developed. And yeah, this only the one with target is to solve this problem, and also many other very good features. In the latest ADB system, the whole lighting area is divided into multiple segments. Each segment is illuminated by one LED. To enable or disable the LEDs will change the shape of the lights. See here, if the LED of these two areas are turned off, then these two car heads will not be glared anymore, will not be dizzied. So this is the whole map of an ADB. So following, we will discuss all these components one by one. The components and its algorithm inside it. So on the camera part, as mentioned before, the first step of the ADAS function is to detect the environment. But how will the detection be implemented? How can the system know that exactly what are around the car? For example, in this picture, there's a car and there's a pedestrian here. And the car knows, and the system knows, okay, there's a car and there's a pedestrian. What's the magic between it? The magic in between is, in most of the case, machine learning, or more specifically, deep learning. Many deep learning algorithms are developed for object detection on pictures, such as ConvNet, ResNet, and YOLO, and many others. But among all this, the ConvNet is the classic one. Most of the other algorithms are developed based on ConvNet. ConvNet, also known as CNN, short for Convolutional Neural Network. The idea behind it is following. Digital pictures consist of pixels. For example, here 500 by 300 pixels. And each pixel is a mixture of three colors: red, green, blue, also RGB picture, with different brightness degree. Each color is in a digital system. Each color is represented by an integer, varies between 0 and 255. So the whole picture will be represented by a three-dimensional matrix. Here we see 500 by 300 by 3. 3 is the three colors: red, green, blue. The first step of a CNN is use the filter to select out the features, and different filters for different features. What are features? What are features? If you look at a car, what makes you think that this is a car? So it can be first the color of it, and the length of it, the height of it, or the curve of it. These are the features. And the filter process is what we call convolution. Basically, the filter is constant three the filter is 3 by 3 matrix, and you take the filter and take a 3 by 3 area of the picture, start from left top, and multiply the elements one by one. First element multiply here, second element multiply here, and then for all 3-dimensional, and add them all together to get the first element of the first feature, and then slide over the filter from left to right and top to down, one by one, or you can also skip some elements to adjust the dimension of the feature. And then after slide all through, the first feature is generated. Then with a second filter, do the same convolution, and then get the second feature. With the third filter, get the third feature. Fourth filter, get the fourth feature. And then finish the first round of feature extraction. To get better result, we can also do a second round. Very similar, but different filters. Actually, in the real project, 10-20 rounds could be done. The more rounds you do, will get more accurate features. After all the features are extracted, they will be fit into a fully connected neural network. This network will decide what the object is, based on its feature. Is it a car or is it a pedestrian? And the result could be, for example, first, it's a car with a possibility of 0.824. Second, it could be a pedestrian with a possibility of 0.021, and other uncategorized. And yeah, this is the basic map of a CNN and deep learning. About CNN and about the deep learning, there are lots to discuss about, but it's kind of out of our scope here. So this is the basic of the CNN, of the object detection. So this is the first component, then second component, motion plan. After the environment is detected, the system knows now how many objects are around him and what are they. Then the system needs to make a decision. What to do next? The object information will be sent into the controller for decision making, and after, a set of commands will send to the actuator. And the object of information are something like this. They will be sent periodically. For example, each 10 milliseconds, and the first round, second round, And for example, in the first set of information, there's a car, and the coordinate is x00, y00. And there's another car, the coordination is 0, x01, y01, and there is a pedestrian with these coordinates, and there's another pedestrian with these coordinates. So, and then similar to the second information. Then what the controller do is, first, it needs to predict the trajectory of the object. For example, is it running towards me or running away from me? And what's the speed? Second, calculate the motion. How should the actuator react? In our case, which LED to turn on or off? Third, to optimize the motion. And because for a given environment, there are many ways for reaction, but only one of them is the best. The algorithm will find out the best. The last, it will schedule the reaction. ADAS system always plan ahead, and the schedule will be updated periodically with new coming object information. The commands that sent to the actuator is generated. Here just an example, because we are using a LD matrix and we'll generate a command matrix. The final component of the ADB system is the actuator, also the LED headlights. The lighting source is a LED matrix, and each LED is responsible for one small area here. And to turn on or turn off the LED, you need a driver. Typically, the driver is a buck boost circuit. And this serial matrix are the commands from the controller, and also they are the flag of the LED. When it's 1, then you turn this LED on. When 0, turn this LED off. And the PWM generator generated PW signals to control the switch here in the buck boost circuit, and this switch is normally MOSFET, so as to adjust the illumination of the LED. So much for the components. But still, something important needs to discuss here: the communication between all these components. How do camera, controller, and actuator communicate with each other? One of the solution is CAN, Controller Area Network. CAN was developed by Bosch Group in 1980s, especially for automotive ECU communication. Now it's the most widely used field bus in automotive. This is the basic structure of a CAN network. Normally, a node is an ECU, but also possible that an ECU contains 2 or more nodes. And each node can send a message onto the bus with a transmitter, and it can also get message from the bus with a receiver block. The messages are sent in broadcast way, which means a message sent by one node will be received by all the nodes. After receiving, the nodes will check if the message should be further processed by these nodes. When yes, the message will be propagated to the core for further processing. When not, you check, no, I don't need this message, then just ignore it, and then get a new message. So this is the basic structure. In order to create a CAN communication net, you need to configure it at the first place. And for example, how many nodes you need, how many messages, how many signals in the message, and what are they? What are those signals? The configuration is stored in a database, a so-called the DBC file. In our case, ADB, the first node, the sensor, and the message it needs to send is message 1 and 2, and message is need to receive is message 3 and message 4. And one point I must emphasize here is, please do not misunderstand the receive here with the receive we mentioned above. And the message left here are the message to be processed. The messages that are not listed here do not mean that they will not be received. As mentioned before, all the messages will be received, but only some of them are important to the nodes. Others will be ignored. And the second node, controller, actuator, and the message part. Each message has a unique ID, and different ID has different priority. And the transmitter is the node that sends the message, and receiver is the node that received and processed this message. Signals are the data that's carried by this message. And in the signal parts, the carrier is the message that carried this signal. After the configuration is done, they will all store in the DBC file. So when you create the CAN network, you need to use this DBC file. So this is the basic of CAN communication at the end of our theoretical part. So see you later in the practice part.